we'll do, we'll talk about the in a bit more detail because I kind of skimmed through it super fast at the end last time. How integers are actually encoded on digital in a digital computer. Okay, and so let me just do my well. Let me start with. I'll do everything for sake of demonstration here in 8 bits, which is car is the data type. Um, and uh, really the only reason for that is convenience because then I don't have to write 32 things. Okay, but the system for 8-bit, 16-bit, 32-bit, 64-bit, they all work exactly the same. It's just more bits. That's all. Okay. So in the 8-bit system, right, I can encode two different kind of integers, okay, and I'll call these int8 and uint8. 8 for 8 bits, u for unsigned, int for integer, okay. And the difference here is whether or not I'm going to include the possibility of there being negative numbers or not, okay. The uint8 is the easiest, so we'll start there. If you have 8 bits, there are 2 to the 8th different patterns of ones and zeros with those 8 bits. And so you can encode 2 to the 8th different things. And the numbers that we assign to those go from 0 to 2 to the 8th minus 1, right? Because we have to spend an encoding on 0. All right, that happens to be 0 to 255. Okay, so if I write down a random bit pattern, okay, so somebody give me a random uh, bit pattern, 8 bits. All right, fine, I'll make it up myself. You guys aren't with it yet this morning, are we? No. Okay, so I've got this bit pattern. How do I understand what this thing represents? Well, the same way that I understand what 1832 represents, right? So if I wrote 1832, you guys understand that there's 1,800s, 3 tens, and 2 ones, right? And you don't actually actively think of it that way anymore because you've been doing this so long that it's just automatic. But when you were in elementary school, you guys probably did kind of think about it that way. And in fact, do you guys remember? I remember this kind of vividly from like 3rd grade. We had like these little wood things, and there'd be like a little tiny wood cube, and that was one. And then there'd be like a tin stick that was like, it wasn't actually 10 of them glued together, but it looked kind of like it was. And then there was 100 sort of plate, and it had grids in it as if you'd glued 100 of those little wood things. And then there was the 1,000, this giant cube that. Okay, do you guys remember that from school? Did they still use those? Huh? Yeah. So, um, okay. Anyway, but now you don't have to really think about it that way. In binary, it's the exact same idea of these uh, place value powers, except they're powers of 2 instead of powers of 10. Okay, so I'm going to have place values of 2 to the 0 up through 2 to the 7th. And let's just write out what those place values are. Well, 1, 2, 4, 8, 16, 32, 64, and 128. Okay. And then let's take my bit pattern that I just made up out of nowhere and decode it. Okay. Well, so this would be, oops, 128 32, 16, 4, and 2, which is what? 180. No, it's not an odd number. 182. Okay. Somebody check Min's arithmetic just to make sure that. Yeah. Um, hmm? Okay. So I have a 1 in the 128's place. So I write 128. I have a 0 in the 64's place. So I didn't add 64 because there was a 0 in that place value. Okay. Hmm? Oh, that's 0B. Yeah, sorry. So you know how like when we write numbers in hex, we put 0x in front of them? 0B just indicates it's in binary. Yeah, sorry. Um, okay, so anyway, 128 plus 32 plus 16 plus 4 plus 2, do the arithmetic, add it up, we get 128, or 182, excuse me. Yeah, okay. So this binary pattern represents 182 as an unsigned 8-bit integer. Yes? Okay, so we could also do this, by the way, in hexadecimal. So what is this same number represented in hex? Well, this part's easy. It's 6. And then what about the other part? 8 and 2 is 10. That's A, plus 1 is B, right? So 0xb6 is this bit pattern expressed in hexadecimal, yes? Well, guess what the place values are in hexadecimal? What's the 6? What's its place value? It's in the ones place. Okay, so that's easy. What about the B? Which position is he in? The 16's place. Because it's hexadecimal, right? So this is equal to B times 16 plus 6 times 1. Well, what is B? 11. Okay, so what's 11 times 16 plus 6 times 1? Ah, it had damn well had better be 182 because it was the same binary pattern. Yeah? Okay, so this, by the way, is, when I've used 1832 as an example and we've been looking in the GNU debugger, and then we look and we see in hex 728 in various places, and we're like, wait a minute, I thought I typed 1832, but what's 728 in hex is 1832 in decimal. Yeah? Okay, so this is the unsigned system. The signed system, we have to do a little bit different work. Okay, I'm going to need more space than I have left on this sheet, so I'm going to go to a new sheet. But before I do that, questions, preguntas, or fragans about this sheet? Yeah, Artie. Oh, I didn't. So the number here is I just made up. 1832 has nothing to do with it. Yeah. The reason I wrote down 1832 is how do you know what 1832 means? It's 1,800 3 tens and 2 ones, right? You understand this place value. So what are the place values in binary? Well, 1, 2, 4, 8, and so on, right? So what are the place values in base 10, like you've been doing all your life? They're powers of 10. What are they in binary? Powers of 2. What are they in hexadecimal? Powers of 16, right? Just all about the base. It's all about that base. Okay. Yeah. Sorry, I couldn't resist. Uh, I could have resisted. Yeah. You know me, Patrick, right? Okay. So, yes, question. Oh, okay. I did some quick mental math. Yes. So, um, to convert into hexadecimal, you take it just 4 bits at a time, right? And if I take those right hand 4 bits, well, I've got no ones, a 2 and a 4, that adds up to 6, right? Then for these 4, I've got an 8, a 2, and a 1. That adds up to 11, okay? And then what is 11? Well, it's B. Because in hex, right, you've got the digits 0 through F. 0 through 9 represent exactly what you think they do, okay? And then 10, I don't want to use 1, 0. I don't want to use two symbols for that, so I use A. 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. Okay. So that's how I do it. You could also just memorize it as 6 is an abbreviation for this 4-bit string of ones and zeros, and B is the abbreviation for that other one. But there is, of course, the method to the madness. And at this point, like I've been doing this for so long that I just kind of think that way, and that's, of course, what I'm trying to get you guys to be able to do, is just to be able to think in hex, right? Or as I told my CS-101 students yesterday, right now you're thinking with portals. You know, the video game Portal. Okay. No, no, they were doing the Towers of Hanoi yesterday. You guys remember that? So, okay, so that's the unsigned system. The signed system is going to work kind of using the magic trick. So let me just, for sake of demonstration, actually, let me just use the same bit pattern that I had before. And through the magic of doing this on an iPad, I can copy and paste. Isn't that rad? Yeah, I know, right? Okay, so I've got this bit pattern, whatever. As in the signed system, we can still encode 256 things. And the sign system, we're going to include some negatives. So we kind of split the difference and we'll say, all right, we'll encode half negative, half not negative. And that allows us to encode negative 128 up through 127. And the reason it's 127 and not 128 is because 0 is in the middle there, and we do have to spend an encoding on him. Okay. So two things about this system. The first thing is I know automatically, looking at this bit pattern, that this is going to represent a negative number as a signed integer. And the reason is, what's the far left bit? It's a 1, okay? That tells me that this number is going to represent a negative. But what I cannot do is decode the rest of it and then just shove a minus in front. That's not the way the system works, okay? So I have a number here, and I don't know what this number represents yet. Okay, I'll show you guys two different ways of decoding it. Okay. Let me just call this number X. Okay. Now let's think back to at the end, well, towards the end last time I did this magic trick where I did subtraction without doing subtraction, and you guys were like mind blown. Yeah. So what was the trick that I did? I mirrored all of the digits and then I added 1. Okay. So 0 mirrored to 9, 1 with 8, 2 with 7, and so on. Okay. Now in binary, how many digits are there? There's just 2. So the 0 will mirror with 1 and vice versa. Okay. So if I flip all the bits, mirror them, then I get this new number. Let me call it Y for right this instant. Okay, so that's the bit pattern of X, but I've just swapped all the ones and zeros. Okay, and I'm going to add 1 to that, and I'll call this new number Z. Okay, just to give it a name. Okay, so how do I do the addition? Well, you guys aren't morons. What's 1 plus 1? 0, carry a 1, right? Because what's 1 plus 1? 2, but that means a 1 in the next position over, yes? Okay, what's 1 plus 0? 1, and then the rest of it, there's no carrying or anything. Oops. So I've got that number there. Okay. So this number, first off, does this represent a positive or a negative? Definitely a positive number because there's a 0 in that leading bit. Okay, which means I can decode it the usual way. So this one, so this, let me say, this represents 64 plus no 32s, no 16s, 1 8, and a 2. Okay, yes.
So 1 plus 1 is 0, like carry 1 to the left, and why is it 1 p.m.? That's the second row from the right.
You mean this entry right there?
Yeah.
Because I have 1 plus 0, right? So I have to add, like when I do the addition in the second and all subsequent columns, I really have to add 3 things: the 2 numbers, and if there was a carry from the previous position, right?
Yeah.
So it's like, how do you add 39 and 47? Well, what's 9 plus 7? 6, carry a 1. And then what's 33 plus 4 is 7, but then you have to add the 8 from the carry from the previous position.
Yeah, that's what I'm asking. It's like you carried the 1 to the left, right?
Yes.
And at first it was 1 plus 0 is 1, but now it's 1 plus 1, so it should be 0. I carried the 1 to the right. You're not having X. You're just having Y.
Oh, yeah. Okay, I see. Yeah, I am not adding X and Y. I am taking this number Y and just adding 1 to it.
Okay.
Yeah. Okay, now we're good?
Yeah.
Okay. Yeah, so, okay, good. All right, so do we buy then that after I do this addition and I get this bit pattern, that bit pattern represents 74? For the positive numbers, everything works exactly the way you think it does, and you don't have to worry about it. Yes? Okay, so if the Z represents 74, then X represents minus 74. Okay, so this procedure of mirroring all of the bits and then adding 1, that's how you compute the negative of something. And if the original thing represented a negative and I compute its negative, what should I get? Some sort of positive quantity, right? So negative X equaled 74, and therefore what should X equal? Negative 74, okay? All right, now how can I test that this actually works? I mean, I claim that this represents minus 74, but how can I double check that I haven't made some horrible error? Okay, I could do that. Or what about if I just add the thing that I claim represents minus 74 to this thing that represents 74? What should I get? I damn well had better get 0. Okay, and if I don't, then that means something has gone horribly wrong, right? So let's do that and see what we get. All right, so the original number was 1 0, oops, let me do this in 1 0 1 1 0 1 1 0. And the second number I got, this number, by the way, is called the 2's complement. Hmm? No, the whole thing. Yeah, the entire bit pattern is the 2's complement of the thing we started with. Okay, now 2's complement, by the way, we use that word or that phrase in 2 different meanings. 2's complement is the system in which we're working. If you have a specific number, you can talk about its 2's complement, okay, which is this mirroring and adding 1 thing, okay? If you mirror, but before you add 1, that's called the 1's complement. So you do the mirroring, that's the ones complement. You add 1, now you have the twos complement. Okay. All right, so let's add these two things together, and what should we get? I hope we're going to get 0. Let's find out. 0, 0, carry, 0, carry, 0, carry, 0, carry, 0, carry, 0, carry, 0, carry. But then what happens to this carry? He's discarded. Okay? And he's discarded because how many bits am I working with? 8 shall be the number of the bits, and the number of the bits shall be 8. There's no 9th bit if we're working in an 8-bit system. Okay? Now, how does this work in 32 or 64 bits? Exactly the same. I just have way more crap to write down. Yes? Okay. So we added all these two things together and we got 0. So does that justify my claim that the original thing ought to represent negative 74? Yeah. Okay. Okay. There are two exceptions, or two kind of weird numbers. Okay. One of them is the number 0. What happens if you mirror all of its bits and then add 1? What do you get? You just get 0 back. Now that makes sense, because what's negative 0? It's the same as 0. Okay, so that number is fine, right? But there is one other number that's a little bit weird, and it's 1 followed by all zeros. As a signed integer, this represents minus 128. That is the least negative, or the bottom end of the negatives. Okay? Yeah? Yeah, it's the most negative of all the negative numbers that we can represent in our 8-bit system. If you mirror its bits and you add 1, what do you get? The same thing. Okay? And so what that might lead you to conclude is that negative 128 is its own negative. And in some sense, that's true. Okay? But what this is exposing is the fact that we're not working in normal human arithmetic. Okay? If you work in normal human arithmetic, how many digits are you allowed to write down for various numbers? Who cares? As many as you want, right? You don't write down a whole bunch of extra zeros if you don't need them. But if you need a 6-digit number instead of a 5-digit number, who cares, right? You just keep writing digits. On a computer, though, we don't have that luxury. If we say, okay, we're going to work in 64 bits, you can't just magically have a 65th bit unless you do some extra work. Okay, so there's sort of an ultimate limit to the number of bits that you can work with, and it basically is however much RAM you have. Okay, so what this means is that our arithmetic system is not the normal human arithmetic system working in the integers, but rather a more circular-like integer system. Does that remind anybody of anything? Well, I did say circular, right? But a very particular circle that you guys use daily. Mm-hmm. This is essentially the arithmetic of a clock, except on the normal timekeeping clock, how many different digits are there? There are 12 of them. And if you will humor me, can we think of that as being 0 through 11 instead of 1 through 12? Okay. In fact, I might want to, maybe after class, I'll take that thing apart and put a 0 where the 12 is, just to, yeah. So, okay, the offness. So the batteries died. Okay. And a couple of weeks ago, it was just sitting there. So I replaced the batteries. Well, this is one of those like atomic clock things where it gets a radio signal to set the time. And so when I put the batteries back in, it started moving as it was receiving that signal. But then it's like super off, right? Um, and it's not like that it's off by a matter of like exactly an hour, because it's off by like several hours, but also a couple of minutes. So I'm really befuddled as to why that happened. And maybe it means I need to just take it outside so it can receive the signal a little bit better and then bring it back in once it's set. Huh? What? Or yeah, or maybe we're all dead and welcome to hell, gentlemen. Yeah. Okay. So yes. Okay. So if you'll humor me, let's think of the clock as going 0 through 11 rather than 1 through 12. Okay. So if I add, for example, on the clock 6 and 6, what do I get? 0. Okay. Not 12. There is no 12. Okay. And that's a system in which the thing cycles around after 12 is sort of the length, if you will, going around the circle. In our 8-bit system, the length going around is 256. Okay, so in the 8-bit scheme, it's like working with a clock that has 256 different positions. Okay, and in a 32 or a 64-bit scheme, it's the same idea, it's just a lot more different positions. Okay. Now, what happens when you go around the clock? Okay. What happens here, for example? I had a final carry that I discarded. When that occurs, we call that overflow. Okay. Sometimes overflow leads you to get the incorrect answer, or incorrect meaning compared to human arithmetic. But it's not always necessarily a bad thing. Okay. And computers do have a way of keeping track of whether or not there was a carry in this final position. Okay. And it goes into a special place called the flag register. This is what would enable us, for example, to, so like, let's take my Commodore 64 computer. Okay. That's in my office, right? My baby. It can only do 8-bit arithmetic. The processor is an 8-bit processor, okay? But you can do 64-bit arithmetic on it. You just have to take it 8 bits at a time. And the reason that you can do that is because you have a thing that can keep track of whether or not you had a carry, and that is in this thing called a flag register, okay? Which we'll talk about more in a little bit. Okay, so let's say that I have the number 127. What would 127 be? Okay, it's that. And you can double check, of course, that if you add up 64 and 32 and so on, you actually get that. Promise it works. Okay, what would happen if I added 1 to 127? So take this number and add 1 to it. What do you get? Huh? You get this bit pattern, which is negative 128. Okay, that would be like on the clock. Okay, what happens if you add 1 to 11? You get 0, right? You've kind of come around the edge of the clock. Okay, now the difference here with the clock is, do I have any negatives up on the clock? No. So if I really wanted to screw with people, I'd label the clock 0, 1, 2, 3, 4, 5, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, right? Yeah? That sounds like an epic plan to really troll people. No, you don't like that idea? Well, okay, maybe I'll just get 2 more clocks and put them next to each other there, and it can be kind of like, we're in the like a nuclear missile command, right, where you've got the different clocks for all the different time zones. Yeah, yeah. Okay, that looked cool. All right, maybe I just need to just put like crap tons of clocks up there, just for funsies. Okay, so right. So this by the way happens if you have the biggest positive number that you can express and you add 1 to it and you're working in the sign system, you swing around and come back to a negative number. Okay? This has actually happened several times and caused death in some instances and mild irritation in others. Okay? of their, this is called an overflow error if this happens and you're not kind of aware that it could happen. Okay, where it has resulted in death is, and this is not quite the integer system, but kind of, the Patriot missile defense system, um, which saw its first operational deployment in the first Gulf War in 1991, which, I mean, none of you were alive yet, basically, right? I watched it on CNN. It was like, wow. So what happened? The Iraqis had some short to medium range ballistic missiles called Scuds. Okay, and they launched a bunch of these, and the Patriot missile system is basically designed to detect and then fire a countermeasure missile that blows up and destroys the warhead in flight so it doesn't actually hit its target. Okay. But the timekeeping system on the Patriot missile battery was such that the longer the system was operational, the more inaccurate its timekeeping got. Okay. There's a long reason, technical reasons why that happened. We'll maybe talk about that a little, after fall break or something. Um, and this isn't really a problem if you reboot the thing periodically, but what do you tend not to think about rebooting your computer when you're in the middle of, oh, I don't know, a war? Okay, so this happened and it detected the missile or the Scud and it calculated a firing solution, but the timekeeping was off by enough that the countermeasure missile didn't actually take out the Scud. It missed, and the Scud warhead hit barracks and killed like 20 something servicemen. Okay, that's bad. Okay. Yes.
Pretty sure there was another example of something similar happening at this hospital that treated cancer patients, and they had this machine that like targeted
The
like
Therac 25.
yeah,
Yes.
it was radiation on
Yeah.
far.
So that was a similar sort of error, but and you guys, I'm imagining that you heard about that from McCart and Lim, right? Okay, because this is another famous instance, well, infamous, I guess, of a software bug that, under a very, very limited set of circumstances, it was in a computer that controlled a radiation therapy machine. Okay, so cancer patients, one way of trying to destroy a tumor is basically to fry that part of the body with a concentrated bit of radiation. And but of course you don't want to overdo it, because if you overdo it, that causes more harm to the rest of the body. And that's exactly what happened in that Therac example, that this limited, very, very limited situation bug, combined with the fact that there wasn't an appropriate safety mechanism built in, that was present on the previous model, by the way, and they excluded it from that particular model to save money, basically. And it zapped a bunch of people, and several people died very much prematurely uh, by getting the wrong doses of this radiation therapy. Right. So this can have deadly consequences if you don't think about it. Sometimes it's just annoying, okay? And this happened to Google maybe about 10 years ago or so, specifically on YouTube, okay? And those of you guys who have taken CS 101 with me maybe remember the example. What was the video that broke YouTube? Yeah, it was the music video for Psy's Gangnam Style, right? The oh 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 Gangnam Style, right? That song. Okay, so the music video for that got so many play counts, and YouTube was encoding the play counts as 32-bit signed integers. Well, what's the largest 32-bit signed integer that you can represent? Would be 2 to the 31 minus 1, which is like 2 point something billion. Okay, that's a pretty big number, but that video got so popular that what happened? It got that many views. And then suddenly somebody added one, and then now it has negative 2 point something billion play counts. and that broke basically YouTube's like the monetization system and all of that, right? Because it overflowed back around to the negatives. So they had to fix it and recode all of the play counts as 64-bit signed integers. Okay, which how many? What's the biggest number you can encode with a 64-bit signed integer? By the way, it'd be 2 to the 63 minus 1, whatever the number that is. Now, to put that number in perspective, though, it's large enough that every person on the planet would each have to watch the Gangnam Style video about 1 billion times per person on the entire planet. Okay, which is to say, it's not going to ever overflow, right? 64 bits is enough. Okay, that's what you think. Yeah. All right, challenge accepted. Right. um, right. Okay. So point being, like that overflow can't happen. Now, because we're working in, or at least for sake of demonstration here, an 8-bit system, this overflow problem is sort of front and center in our mind because there's only 256 numbers here, right? That's not a whole lot to be able to work with. Okay. Um, but ultimately, any computer arithmetic is going to have this kind of limitation. It's just that nowadays we work in 32 or 64-bit arithmetic, and we don't confront this problem as often as we used to. Okay. Okay. Does that kind of make sense? Yeah. 4.5 billion. That I'm not sure about, or if like there was just some sort of error, or if YouTube's engine crashed. Yeah. So suddenly, Psy went from YouTube owing him a lot of money to him owing YouTube a lot of money, right, for the negative play counts. So yeah, yeah. So like I said, this can have deadly consequences or just mildly irritating consequences. Um, and what you know, you guys as computer scientists or computer science majors, right? When you guys go out into the workforce and you're programming or doing something like this for a living, you need to be cognizant of these incidents that have happened. And when you're designing software or working on particularly a big software project with, you know, possibly hundreds of other people, right? Be cognizant that you can't understand every part of every system in that giant ass program. Okay, but you have to have be cognizant of the parts A you're working on, and B, there needs to be some sort of review procedures in place to catch these kinds of things before you deploy it to the battlefield or to a hospital or to, you know, whatever. Okay. Um, you know, because if you make that software mistake and people die, I mean, you're kind of responsible. Maybe not legally, like the company might be the legally responsible entity, but you just killed people. I would hope you would get fired for something like that, right? Yeah, no, I would hope that you would get fired for something like that. Okay. Well, yeah, I mean, it depends, right? Obviously, on the details, but you know, these kinds of issues are happening even today, right? So, how many of you guys have been kind of following Boeing with the 780, or sorry, the 737 Max? No. Okay. Well, uh, no, that was a seven. That was a 777, and the Malaysia flight, like in one case, was uh, Russians shot it down. Uh, well, there are two Malaysia flights. There's the one that went missing, uh, and in the that was flying from Indonesia to China, I think it was, and then it just kind of made this, you know, U-turn and went out over the ocean. Basically, never has been seen since. Um, but then there was another one that was flying over. This is uh, before Russia actually invaded Ukraine, but in Donetsk, which is one of the eastern separatist regions. Um, a Russian anti-aircraft missile battery that was in, well, it was in that separatist region, shot down this another Malaysian airliner, um, and they claimed they thought it was a No, they knew exactly what they were doing. Um, yeah, well, um, and because Russia has nuclear weapons, they get away with this kind of crap, right? Right? Huh? Well, I mean, to be fair, right? The U.S. isn't bloodless on this. We have shot down civilian airliners by mistake too. It actually happened during the Gulf War. Um, we shot down an Iranian passenger plane by mistake. Um, so, huh? Well, the Iranians weren't part of the conflict, right? The Iraqis were. Um, start traveling by boat. Yeah, well, uh, yeah. Then the Germans show up with a submarine or something, right? And yeah. Okay. So, um, so this is how this all works, kind of pen and paper. And let's now talk about this from a computing perspective. Okay. Okay. So good. So any other questions about the paper end of this? No. Good. Okay. So I'll actually give you guys, this will be kind of a weird assignment because it'll be one that I'll have you do on paper to do some of this arithmetic just to kind of make sure that you got it straight. Okay. Um, all right, let's go over to the Pi and let's actually do some programming and kind of look at how this is going to work in assembly. Okay, so let me make a new folder here and I'll call this folder arithmetic. And of course, I just created it in a folder. So let me try it again. Nope, that's not what I want to do. Oh, for the love of God. We'll just do it that way. Okay, so let's kind of look at how the arithmetic or how addition, subtraction work. Subtraction, by the way, is, you can think of it in two ways. You can think of it as adding a negative, right? If I want to do 7 minus 5, what I can really do is do 7 plus negative 5. You don't have to do that in a computer sense because, well, two things. Um, there is actually a hardware subtraction unit in the processor. They're hardware addition, hardware subtraction, and of course, modern processors also have all kinds of things to do, multiplication and floating point and exotic stuff like that. Okay, but let's just concentrate on the addition for right this moment. And let me change this to 64-bit ARM assembly, not 6502 assembly. Okay, so that's the usual shell of our program. Okay, there are actually 4 addition instructions on ARM, okay, and they are as follows. We have add, we have add C, we have add CS, and we have add S. Okay, so what all these do is add, well, adds, discards any carry, disregards previous carries. Okay. Add S adds, but does not discard a carry, disregards previous carries. Okay, and then the C's take into account a previous carry. Okay, so add C, or actually it's just ADC. There's not a second D in it. Okay, so there basically are four combinations, right? I can, if I get a carry for an operation, I can set my carry flag or not. There's two choices. And if the carry flag is set, I can take that into account or not. There's another two choices. And those choices are independent, so there's four combinations. Okay, so the carry flag, what that does is if the carry flag is a 1, like, so let's say I add 5 and 7 and my carry flag is a 1, okay, and I do add C. What's 5 plus 7? 12 plus 1 is, okay, so if I'm taking into account a previous carry, and that happens with the either add C or add CS operation, if the carry flag is a 1, I add that in. If it's a 0, well, then I'm adding in a 0 and that doesn't change anything, okay? The S's set the carry flag after the operation is complete, okay? This, by the way, is how I can do bigger arithmetics than 64 bits, okay? I just take it 64 bits at a time. Well, or 32 bits at a time, right? But I can do 64-bit arithmetic because I've got the X registers, right? So let's say, and maybe that's actually the way to demonstrate this. Let's say that I was using 32-bit registers, and let's pretend temporarily that our machine can only do 32-bit arithmetic. How could I do 64-bit arithmetic if I don't have a 64-bit machine? Well, what I have to do is think about it in two chunks of 32 bits. Okay, so for example, let's move a number to, let's do, move something to W0, and let me do a 32-bit number. So let's do, let me do that one. That, by the way, represents -1. Okay, because F is all ones. Well, what happens if you flip everything? You get all zeros, you add 1, you get 1. So then all ones is the bit pattern for -1. Yeah? Trust me, it is. Trust me, I'm a doctor. Okay? And I'll go ahead and put the pound sign there. Okay, let me also move to W1. Well, let me just put the number 1 there. Okay? And then let's make a string, and let's call this oops. Actually, you know what? I don't want to do that many. Let me just do 1 for now, and we'll modify it up a little bit later. That is weird. Yes. That is really weird, gentlemen. me just type it. That's really weird. No, because that's part of the string. So, okay, whatever. This is just VS Code being VS Code. Okay, so let's add these two things together. Okay, and I'm going to so let me do add W1 as my destination. W1 and W0 are my two operands. Okay, and then I need to move, well, sorry, LDR, X0 with what? The address of the format string, and then I'm going to print. Okay, all right, and so let's assemble, run this, make sure that I haven't screwed anything up, which of course is certainly always possible. I'm going to go ahead and put in the debugging flags. Okay, that's a warning, not an error. Okay, so what it was the result of the addition? 0. Okay, now that makes sense because what did I add? I added 1 and -1. Okay, so if you didn't believe me that that number FFFFFFF was -1, well, have I convinced you now? Hopefully. Okay, so all right, we got the correct answer, yay. But let's look at if I run this in GDB. So I need to change directory to here. Oh, I have to run it first. Okay, so let's look at the registers. So I'm about to do the addition operation, but it hasn't actually taken place yet. So what do I see in registers X0 and X1, which really in this case means W0 and W1? What do I see there? Yeah, so I see 1, and then I also have this other thing, all S, that represents -1. But over there, what does it actually display? Not that, okay? But what it's displaying there is interpreting it as a 32-bit unsigned integer, in which case the largest number you can represent is 4-point-something billion. That's the number, okay? So the thing on the right is it's trying to be smart and decode this for you, but it doesn't necessarily know whether or not you're treating it as signed or unsigned, okay? And so it may not look the way you think it does. Now, it doesn't mess this up with the 64-bit ones. For example, look what just so happens to be in X8 is the 64-bit version of all ones, and it does correctly decode that one. Okay, whatever. I think the reason it's doing this is because the 32-bit stuff, like this really is a 64-bit machine, okay? And so, like, yeah, okay. All right, so are we cool that those are the two input numbers, and I'm about to do the addition. Now, there's one other register that I want to point out to you, which is down here at the very bottom. There's some special ones. There's this thing called the stack pointer, okay, which we'll talk in glorious detail about later. There's this thing called the program counter. And then there's 3 registers here that are status registers. And the one that I want to point out here is CPSR, which is the CPU's basically status register. And it has this number in here. The number itself is not really relevant, okay? But what is relevant is certain bits of it, okay? Whether or not certain bits are a 1 or a 0, those are what we call flags. So if I did an addition and there was a carry and I discarded it, then I could program this to raise the flag to signal, hey, a carry just got, there was a carry, okay? On some systems, so for example, on my Commodore, there's only one add command, okay? It always takes into account a previous carry, and you have to use a separate instruction if you want to clear the carry, okay? But on ARM, we happen to have 4 add instructions. So we're going to do this exact same exercise, but with all 4 of the add instructions. Right now, we're using vanilla add, okay? So the C and the Z flags are currently set, okay, which is how you read this. So if you see, there's 4 letters that you'll see here: C, V, N, and Z, okay? So carry, overflow, negative, and 0. Yes? Okay, so let's do the actual addition and see what happens. Okay, and then it's about to get ready to print, but if we look at the registers now, then what has happened? Well, what's the result in W0, the result of this addition? 0, okay, and that's what we were expecting. Have the flags changed? No, they were the same as they were before. And the reason that they didn't change, because we just got a result of 0, yes? We also technically had an overflow in a 32-bit sense. But the reason the flags didn't change is because which operation did I use? Which add command? I just used add, not add s. Okay, so let's redo this, but with the add s instruction instead of the add instruction. Okay, is that all right? Okay, so if I change this to add s, okay, that's literally the only change. Let me reassemble it. Do that here. Oops. Okay, so the registers are, I'm about to do the addition. Everything looks exactly how it was before. Okay, but now let me do the addition. So the addition just happened. Oops. And what happened to our registers here? We still get 0. All right, now the carry flag and the 0 flag got raised. Okay, they happened to already have been raised. So does it look like anything happened to my registers? No. Okay, and that's only because those 2 flags happened to already be up before I did this operation. Okay, so let me demonstrate how I know that that's the case. Let me go back into here and let me change this to add CS. Okay, so what this will do is take into account if the carry flag is set and also set the flag after the operation is complete. Okay, all right, so let me reassemble it before the operation and then sets it if needed. Right, okay, so it depends on whether or not I'm doing add S or add CS, right? So, because if I did add C, it would take into account what the flag currently is, but it would neither set it nor not set it depending on the result. Add CS will do that extra step of setting the flags, right? So you have all four combinations of being able to set flags or care about their previous status, okay? All right, so let's reassemble it, and let's go into GDB. Okay, so the registers are loaded with the appropriate numbers, okay? And it just so happens that the carry flag and the zero flag are both, right now they're both set. Yes? I have not actually performed the addition, okay? So the add instruction is about to get executed. What do we expect to see as the result of the add operation here? What are we adding? We're adding 1 and -1, right? So what do you expect to get? 0, but we're not. What did we actually get? We actually got 1, and the reason was, what was the carry flag before I did the operation? It was a 1. It was set, okay? So what I was actually adding was -1 plus 1 plus the carry flag. And because the carry flag just so happened to be set before I did this, that's why I got the result of 1 and not -1. Okay. Now, the other thing is, what instruction did I use here? I did add CS. Okay. So I set the flags after the result of this operation. Okay. When I added these two numbers, did a carry occur? Yes. And look, the carry flag is set. But what was the result of the operation here? What was the sum? 1, not 0 like it was before. Okay. And look what flag is no longer set. The 0 flag, because I didn't get 0 as my answer. Okay. So does this kind of make sense? There is, yes. So good question, right? If you want to deliberately set the flag to be a particular thing, there is an instruction to do this. Okay. I'm blanking on exactly what it is off the top of my head in ARM. In 6502 assembly, it's clear carry, CLC. And there's another one called set carry, which you have to basically do. If you're about to do an addition for the first time, you need to clear the carry. For all subsequent bytes, you keep it. And for subtraction, you have to set the carry initially. So yes, so there are instructions to change the flags. The other thing, though, is, well, we have 4 add instructions. Okay, so if I wanted to do, for example, a kind of poor man's 64-bit arithmetic on a 32-bit machine, how would I do that? Let me go back to the iPad and kind of sketch out the idea, and then the programming is sort of a separate exercise. Okay, so let me go back to here, and I would do, so if I wanted to do poor man's 64-bit addition using only 32 bits, what I would do is I would think of a 64-bit. So let's say that I want to add 2 numbers together, and they're both 64-bit numbers. I'm going to think of them as being 2 32-bit chunks. Okay, so this would be 32-bit and 32-bit. And so what I would do is let me call this A, B, C, and D, just to give them names. What I would do is I would add S A plus B. And then I would do add C or add CS for C plus D. Okay, so what this would do is when I'm adding my lowest order positions, I don't care whether or not there was a carry beforehand because I'm starting arithmetic from scratch. But I do want to set the flags. Okay, so let me maybe give you an example of how this would look. Let's take how would I write -1 in 64 bits? It's just a crap ton of F's, okay? And 1 would be a bunch of zeros and then a 1, okay? So if I had, say, 1 would be 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, 0, 0, 1. I'm writing this in hex, not in binary, okay? -1 would be F, 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 F. Okay. Coincidentally, that happens to look a lot like the grade book for this everybody in this class, right? Not really. I'm kidding, of course, right? Huh? Huh? The string of Fs. Yeah. It's kind of like an Oprah, right? You get an F and you get an F. Okay. So what I would do is let me again label these. So let me call this chunk A, this chunk B, this chunk C, and this chunk D. Okay. I'm going to add A and B, and I'm going to set the flags. Okay, so let me actually write this in proper, well, let me just write it like this. Okay, so what is the sum of A and B? So remember, A is just this set of numbers, and what's that? Okay, what do I get if I do that? 0. But there was a final carry, and if I'm going to take that into account, I need to set the flag. Okay, and I know that I set the flag because I used the add S instruction. So the S sets flags after the result. Okay, now are we clear why there is actually a carry there? Okay, because what is FFFFFF, right, in binary? It's just a crap ton of ones in a row. And if I add 1 to that, what happens in the final bit position? 0 carry, 0 carry, 0 carry, and that cascades all the way down to the 32nd bit, and then I get 0 and a final carry that would go into the 33rd bit, but there isn't one. So it sets the flag. Okay. All right, then I need to do add C or add CS. I'll just do add C of the number C and D. Okay. If I just add C and D as they appear, what would I get? Well, C is just a bunch of zeros, so that doesn't change anything, right? If I add these two things, what am I going to get? Just F, 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 F. Okay. But if I take into account the previous result, what this is going to do is add C, D, and the number 1 from the carry flag. Okay? And what do I get if I add 0 of crap ton of F's and the number 1? I get 0. 0, 0, 0. Okay, so my sum would be 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, 0, 0. Is that what I would expect to get? Yeah, okay, because what was I trying to do here? I was effectively adding 1 to -1. Okay, so let's just kind of recap real quick. What have we done? In the lowest order chunk, I don't care about what the carry flag currently is, but I do need to set it. On all subsequent chunks, I need to take into account what it was on the previous operation and then set it. For the final one, I can either set it or not. I would go ahead and set it. So I would probably do add CS here just for posterity. Okay. All right. So more new diabolical assignments coming soon to a Canvas near you. All right. And I'll get the info up about the midterm. Yes, you will do that in class on Tuesday. Okay.